had a few questions during the break, and I'm very pleased that you asked questions. You're also welcome to ask them during the lecture. One of them was the hysteresis we observe, the change or the difference between the desorption and the absorption. And it was correctly mentioned that the first time you dry out a sample, you will have a damage to the pore structure. So the difference between the first desorption curve and then the adsorption curve you obtain afterwards, that's partly due to this impact of the pore structure, where you can have smaller bottlenecks for the entrance to larger pores, and that you actually change the pore structure of your material. This is something I'm going to mention later in the next lecture, because it has an impact on the porosity we measure on dried samples. So we need to know how actually to deal with this. The other question I got, it was, how do you actually get these various relative humidities? Well, if you have an instrument, a cupboard, where you can change the relative humidity by mixing dry and wet air, you can do that. That's what you use for dynamic sorption measurements. But they're quite expensive, and you can only have one sample. It doesn't take that long time. But there are other ways of doing it, and that's to use desiccators with salt solutions. And then you have different salt solutions, saturated salt solutions. And depending on which salt solution you will have an equilibrium with the vapor in the air above the salt solution, giving a different relative humidity, or given relative humidity. So in that way you can actually select different relative humidities. And typically when you're doing experiments like that, you will choose salt solution where the impact of temperature is not that big on the relative humidity in the vapor. There's a lot of information. And then you would also choose salt solutions which are not poisonous. Other considerations. Okay. Other questions? Yeah, please. Could you please use the microphone, because then...
Yes, you have just mentioned the time scale on which this adsorption experiment will go. I learned in a course in the past somewhere that the time scale of the adsorption experiment is always a bit critical, because one never knows when it's actually finished. So how it is dealt with that there?
Well, normally you would measure the weight change as a function of time, and at a certain time you will see that there are only small changes. So that's how you deal with that. You have equilibrium.
So essentially one sets an arbitrary threshold.
Yeah.
Okay.
And at the same time, you need to consider if you have prolonged hydration or if you have carbonation, and then that's something to deal with. And that will be talked about later also. Yeah. But good point. Okay. So now we have talked about that we can actually predict the phases, the porosity, not the the fine porosity and the coarse porosity, not the pore size distribution. We are not able to do that yet. But that may not be the porosity that we actually end up with in the structure. And it could be that there are features which have an impact on that. So let's have a look. Well, first of all, as the hydration process takes place, we have this chemical shrinkage causing drying out of the coarser pores. It starts with the largest pore drying out first. And this is illustrated by this figure, where we have a low degree of hydration and we have a few pores. That's so the dark gray, that's the cement grains. The lighter gray, that's the water. And then the white here, that's pores. So we have a reduction of the amount of pore water due to the binding in the hydrates. We have an increase of the amount of the solid material, and we have a refinement of the pore structure. That's what's happening. Then we have an increase of empty pore volume due to the chemical shrinkage when hydration proceeds, and we have a decrease in the meniscus, or the radius of the curvature of the menisci. And this is illustrated here, where you can see that now we have also smaller empty pores, and the radius of the menisca is decreased. And then, depending on the material, we will have a bulk shrinkage. The whole bulk will shrink due to tensile stresses being set up here, where we have the meniscus. This is what we call self-desiccation shrinkage, or autogenous deformation, or autogenous shrinkage. For ordinary concrete, it's not a problem, conventional concrete, and you will read the textbooks from, some of the textbooks from 95, where it says autogenous deformation is no problem. But increasingly, when we are using concrete where we have very fine materials, we have silica fume, for instance, where we have a lot of fine materials setting up small menisci, and we have improved packing of the material, and we have this large chemical shrinkage, we actually may have autogenous deformation with Gibbs problem. Due to autogenous deformation, well, when you're casting a structure, you set up limitations on the difference in temperature because you want to control the volume variations, so you don't have cracking. If you have autogenous deformation, the temperature limits have to be decreased. And that means that you need to have more cooling inside your structure when you're casting a large concrete, and that's a lot of money. So you want to consider that also because, well, if you get cracking, you need to repair it. A tunnel with cracks is not the tunnel you want. There's another thing you need to consider if you want to make samples and you want to have a given structure. This is work by Del Benz and Paul Stutzman from NIST, and they were working with the impact of curing, the amount of water available during curing on the pore structure. And they came up with this schematic graph showing here we have cement grain unhydrated, hydrated, we have water, and then we have some reaction products. If we have a system where we have sufficient water, it's saturated, so we have water coming in. The hydrates outside the grain, they can precipitate where there's sufficient or large amount of space. If, on the other hand, we have a system where we have self-desiccation, the large pore here is empty, no water, and the hydrates will precipitate other places. If, for instance, you consider these two structures and you are having chlorides ingressing, you will see that in this situation, chlorides can actually go much more easily in than in this. They measured it differently. They measured with a technique, low temperature calorimetry, or differential temperature scanning, where you freeze the sample and then you monitor when freezing starts. And what they saw that initially, or after some hydration, they had this, for systems which were seal cured, they had a finer porosity. At a certain time, it seemed that the porosity repercolated, became connected again, the larger porosity, and maybe due to microcracking. But that means that the way you cure the sample has an impact on the porosity you get. Even though if you were just modeling this, it would be the same system. Then, as Karen showed the other day, also the temperature has an impact on the porosity. We have the same mixed composition, we make the same paste, but we cure it differently. And due to the difference in the density of the CSH, we will end up with different capillary porosity. That can be modeled if we do the thermodynamic model. It could also be modeled if you do the mass balance and have the molecular, know the molecular volume of your sample. But if you're just using Powers' model, it will not show up. Then another issue is that if we're considering, we want to know the volume of the larger pores because we want to have an estimate of, for instance, the ingress of water or the ingress of chlorides. Then if some of the pores are ending up as so-called Hadley grains, these were the grains which became empty or partly empty. The initial cement grains, here you see one. You've had a cement grain. And the hydration products, you have a small rim here, but else the hydration products has formed outside the initial grain. And here you have a so-called Hadley grain where you have porosity, which is almost not connected to the remaining porosity. It's connected through the CSH. So if you have material going through the sample, they will not easily go through this porosity, part of the porosity. And the amount of Hadley grains, that will vary through the hydration. Here you see some sketches from some of Karen Scribner's work, and you have the unhydrated grains here, different size, and then after 1 day, this is the small grain is fully hydrated, and on this sketch it's empty, partly empty. So here we have a large Hadley grain pore. Here we can see that we have a rim of the two others. When the samples are mature, we still have this pore, closed pore, in the small, where the small grain was. Some in the middle size grain, but none in the large size grain. And here you then see porosity where you have some rims here. In this backscattered image, all what is dark is the porosity. Okay, then another feature, that's the interfacial transition zone. And the interfacial transition zone, this was a zone just next to the larger aggregates. Initially, when you make your mix and you have the larger aggregates, the cement grains cannot pack the same way just next to the aggregates. We have this wall effect. And then the hydration starts. This is what you see here on mixing, that you have a looser packing of the particles. So this is the volume fraction of solids. No, let's have a look. This is the volume fraction of the porosity as a function of the distance from the aggregate. And you can see here that we have a larger porosity just next to the grain. Then hydration starts, and we will have more fine grains just next to the, due to the packing issue. So we will have a larger change in porosity just next to the aggregate. But even though we see that we have a difference in the porosity close to the aggregate and far out, this is this area where we have the constant porosity we call the bulk. This is something you should consider, for instance, if you're making a concrete and then you want to make a companion sample with a paste. And then you have to consider if you want to have a companion sample which actually has the same properties as the bulk, or if you want to illustrate the properties of the interfacial transition zone. And you have to choose a different water-cement ratio then. So the water-cement ratio in your bulk is lower than the water-cement ratio in the interfacial transition zone. You can make some calculations on the amount of material in the interfacial transition zone if you consider the width or the thickness of this zone, and then if you know the surface of the aggregates. And in a normal concrete, you can actually end up with half of the paste being in the interfacial transition zone. You can also consider that if you have a lot of this interfacial transition zone and it's interconnected, chlorides will not bother to go through the bulk. They will actually go through the interfacial transitions then. Okay. There's a lot of discussion also on this. Then the next is, now we're moving up. You saw some of these slides yesterday? Or not slides, but sections. A thin section. So this is an epoxy impregnated thin section. It's 20 microns thick. It's important that it has the same thickness or the constant thickness because we use it for assessing the capillary porosity by the intensity of the green color. What we have here, well, it's a fluorescent impregnated, and the yellow, that's the voids. This is an aggregate. The green is the paste, and what we see here is that it has a very even green color, so it's a homogeneous capillary porosity. And the green, the intensity of the green color, it gives us information on the capillary porosity. These are the air-entrained voids to give frost resistance, and it's also quite well distributed. We want these distributed so the water and the ice can move into them when it's, the concrete is subjected to freezing. Okay, same mix, not so good. We have inhomogeneous capillary porosity. Maybe due to improper mixing, maybe due to problems during the casting. But at least you can see that this is not what you expected. If you model the porosity of this, you would, and then use that as information on the rate of ingress, you would not get what you would, something which was comparable if you were testing the sample. This is kind of tests which are sometimes done in connection with pre-testing of materials or mixes, so you actually are sure that you can get a homogeneous mix. And it's also type of investigations you would make in a structure which has been cast. And I'll show you some examples here, because here you can see some paste separations, and it's typically due to movement of the paste before it got sufficient stiffness. And here you have, well, highways through the paste or the concrete. Here we have adhesion cracks along the aggregates, also giving a very inhomogeneous structure. And in the last one we have microcracks. Microcracks which could be due to self-desiccation. So initially you have a very rather homogeneous mix here, and it's very dense, but you have the microcracks. And what's the impact of these microcracks on the transport? Okay, any questions? So, a few examples. One thing you could say that when we have a structure, well, first of all, the impact of moisture on the various transport mechanisms is that here you have the rate of the flow as a function of the relative humidity. If we have gases, they will be transported most easily if we have a dry material. If we have ions, they need water to be transported in, if we're not considering that the ions actually are transported together with the water. But if it's diffusion or migration, we need water. And then the rate of transport of water, here we have vapor transport and then capillary suction. So that would also increase in rate. Now, here we have data from a structure. This is a motorways in just north of Copenhagen. They were doing some experiments to see the performance of different mixes on these edge beams. This has been a huge problem because the edge beams are exposed to chlorides and they are getting damaged much more easily than the rest of the bridge. And at that time, they chose to have edge beams elements. They have, the road director have actually changed the setup. Now they are casting the edge beams together with the rest of the structure, and then they're using stainless steel to limit, to hinder reinforcement corrosion. So we have some examples here. This is the water, well, it should be W, water to ratio of the cement plus 2 times the silica fume. This is what is called the equivalent water cement ratio. And it's the efficiency factor 2, which is used for silica fume here. The efficiency factor is discussed in connection with standardization work. And for a time it has been 2, but it's of course based on the property you're considering. Is it strength or is it durability? And at what time you're considering. Is it 1 day, 2 days, 28 days? Which value is reasonable? And the efficiency factor describes how much, if I take 1 kilo, or if I add 1 kilo of the material here, silica fume, how many kilos of cement can I take out of the mix and get the same property? Okay, so we see we have these equivalent water cement ratios, and we have an increasing amount of silica fume to cement. We have no silica fume, 10% and 20%. Then these are the apparent diffusion coefficients. They have drilled out a core, they've taken it to the lab, they have ground it, have samples from different depths, analyzed them for chloride and getting a chloride profile, and then they have calculated the diffusion coefficient, which would give rise to this chloride profile. This diffusion coefficient, well, it includes the combined effect of exposure, time, temperature during the whole service life, and it also includes the binding, the possible binding. So what we see here, we have 3.5, 1.5, and 0.9, not that much difference. Then they have taken cores from the back, or the non-exposed part of the concrete, and they have saturated them, as we do when we are doing chloride tests in the lab, and they have exposed them to chloride, so-called bulk diffusion test, where you have the sample, you expose it from one side for, I think it's 35 days, and then you do the same again. The grinding and the determination of the diffusion coefficient. And you can see a huge difference. For the larger here, you have a much higher diffusion coefficient. And why that? Yeah. It's the... Could you speak up, please?
I say that there is the reaction to Svanegon if you add the silica fume.
Yeah, yeah. But the difference between what we see in situ and what we see in the lab, that's much bigger for this sample, where we have the no silica fume and the highest water cement ratio. And this is the way, if we are doing trial tests. If I was asked, well, which concrete would you propose, or will you document your concrete? I was to use this laboratory test. Well, what we thought was that when we do the laboratory test, we actually saturate the sample. We fill all the porosity with water, whereas in situ, it may not be that their samples are fully saturated. And it would be the coarsest porosity which we would saturate on the lab samples, and we have much more coarse porosity in the sample where we don't have silica fume and where we have a higher water cement ratio. So that could be an explanation. It's relevant because when you have the concrete with low water cement ratio and silica fume, they may not be that easy to work with and we may have the risk of autogenous deformation. So if you're just choosing your mix based on these lab tests, you may end up with something which is not that easy to work with, and you may create other problems. So that's why we actually started looking at this. Yep.
That's great. What's the pre-diffusion coefficient for chloride in a more or less diluted solution in a beaker or so, just for comparison?
The
diffusion coefficient for chloride just in a beaker. So
yeah.
I'm asking because I'm interested in the effects, in the wall effects of the porosity also, just to have a comparison with the values.
It's the diffusion. You can assume that's what we did in this. That if we assume that the chloride's diffusion in the capillary pores is comparable to the diffusion in bulk water,
Okay.
but the diffusion coefficient in the gel is much, much slower. And it was based on work by Edgar Bose from NIST. It's 400 times lower, so nil. Yeah. And then you need to know the volume of capillary pores. Yeah. And that's why we have started to look at that we have these two types of pores, or pore sizes, ranges of pore sizes. That was the assumption. And that we have diffusion coefficients comparable to bulk water in the capillary pores. Oops, yeah. And very low diffusion coefficient in the gel pores. We knew the sorption isotherms. Well, first of all, we had the material. We could estimate the volume of capillary pores and gel pores. And we also determined the amount of gel matrix where we could have transport. We determined the amount of paste in which are just composite models, and the amount of mortar depending on the amount of aggregates. Or the diffusion coefficient in the gel, in the paste, and in the mortar. And we were working with mortar. We made some samples to see the impact of the degree of saturation on the diffusion coefficients. When we did that, we used here the composition of the mortar, rapid hardening Portland cement, water cement ratio 0.5, and a maturity of 6 months. That means that during the testing, we don't expect much change. That was why. And we saturated the samples or conditioned it in different ways. One was vacuum saturated. One was stored in 65% relative humidity, and one in 85% relative humidity. And then we knew the sorption isotherm, so we could translate the relative humidity to degree of saturation. We exposed the samples to chloride. Here they were exposed to a solution. Here we exposed them to a brine, a very concentrated solution, for a few hours, and then removed the water again to keep them at the right relative humidity. And then you can see that, and then we predicted the diffusion coefficient based on these volume considerations. How much capillary porosity would we have after 6 months in this mix? How much of the capillary porosity is saturated at the condition we are looking at? And these are the simulated values, and then we measured the chlorine ingress. And it seems for this concrete to work quite well. What you should look at is, or consider, is that we have a fairly high water cement ratio. That means that we have an interconnected capillary porosity. If the capillary porosity is not interconnected, you can't use this. But in that way, we could actually explain the difference between what we observed in situ and what we observed in the lab. Okay, any questions to that? Then the next example, some considerations we could look at is that when you're casting concrete, there are guidelines as to for how long you have to protect the concrete. You protect it to that the water will not evaporate, to ensure that you have a sufficient hydration of your sample before the concrete may leave. And this is an example from the Danish standard. It's an execution standard, and now it's overtaken by the European standard. But the example can be used. We have different environmental classes: the passive, moderate, aggressive, and extra aggressive. So passive, that would be in here, where we don't have any problems with the deterioration mechanisms. Extra aggressive would be the edge beams, for instance, or splash zone in marine structures. Then, preferably, there's a requirement, or preferably you should determine the degree of hydration, but that's not practical. And then instead, there are requirements to the age, the maturity age. Have you heard about maturity? Okay. Maturity is the relative time. It's used, for instance, in connection with such guidelines or requirements. It's the temperature, or it's the degree of reaction at the same. How should I put it? It's the degree of reaction compared to here. If you take this, 12 hours at 20 degrees. If it's in Europe, it would be 20. In the US, sometimes you will see that they use 23 degrees, but it's a reference temperature. And that takes into account that if the structure is exposed to low temperatures, you need longer time because you have the degree of reaction you actually need. Or if you have higher temperatures, you can proceed after shorter real hours, or fewer real hours. Then you will see that you also have, here you have increasing, requirements to increasing degree of hydration, and that's reflected in guidelines giving increasing amount of maturity hours. So 120 hours at 20 degrees, or double up at 10 degrees, or the half at 35 degrees. No. No. Arrhenius equation is, yeah. And then the activation energy is different. It depends on the mix, and it also depends on the temperature. Yeah, but it's not linear. It's more exponential, actually. And there are different ways of calculating it. Yeah. Also. So what we see here is that if we take, well, there could be a reason we need a certain capillary, or we need a decrease in the capillary porosity to a certain limit, depending on the type of exposure. So if you look at this, we use the Powers model. Here we have added chemical shrinkage, capillary water, and we get the volume of capillary pores, which we can estimate as a function of the initial water-cement ratio and the degree of reaction. And here we have the degree of reaction and the initial water-cement ratio. If I only have a requirement that I should have maximum 0.4 capillary porosity, volume fraction, it's sufficient to go to the black line here. But if I have a requirement which is at maximum 0.2, 20% capillary porosity, I need further hydration. So you can see for 0.4 water-cement ratio, I need a degree of hydration at 70% approximately. And if we looked at this table, here and take an example where it's a concrete to go into aggressive environment, and we have a water-cement ratio between 45 and 40. Take it here, move up, and have this 85. We see that it actually compares quite well with the 20% volume fraction of the capillary porosity, or 20% capillary porosity. It's in some of the literature said that if you have less than 20% capillary porosity, it's disconnected. That depends on at which level you're looking at it. But you can see that if we, for instance, look at the requirement here to extra aggressive, we will have less than 20%. On the other hand, if we take another example, and that's a concrete to be used in a moderate environmental class, we accept or we are allowed to use a higher water-cement ratio, and we can see that compares to 40%, maximum 40% capillary porosity. So it gives you an idea of what's the background for the requirements. If you were using a different concrete, you could argue that, well, I don't need to protect my concrete for that long, if you were the contractor. Or if you were using a different water-cement ratio, different rate of reaction. So you could go into more detail and optimize your casting or execution. Then the last example, that's on optimization of cement blend using thermodynamic modeling. And this is from a PhD project undertaken by Claudia de Wert at the Norwegian University of Science and Technology. And she defended a month ago and kindly brought me these slides. So she worked together with Barbara Lottenbach from EMPA, and one of the things she did was to model, she was looking into the possibility of improving blended cement by intermixing fly ash and limestone. And here you have an example or a graph showing the volume fraction of the various phases of mixes where you have 65% cement, OPC, and then you have 35% of fly ash and limestone, and with increasing amount of limestone here. So from 0, only fly ash, to 35% limestone. And you can here see that the phases change when we add increasing amount of limestone, and you can also see that we have this increase in volume of solids, which gives the higher strength. And, well, depending on the alumina content of the fly ash, you can optimize the limestone content. And what they found with these materials they were looking at, this Portland cement, this fly ash, they found that with 5% of limestone, they got the best mix. In this, you have to make some assumptions, and one of the most important is the degree of reaction of the materials. So, questions? What to bring home? Well, we have the pores in the material, in cement-based materials. And the range from nanometer to micrometer, and when we have the concrete, we also have larger pores. The definitions vary, don't forget it. And we can estimate fractions. At present, most of the estimations are divided into capillary and gel porosity. And the amount, the size, and the distribution affects the engineering properties. And then at the back of the the presentation, I've added a lot of references. Okay, thank you. Yes, they will be uploaded. Other questions?